All right, so now we move on to the final exam review, Unit 4, which is equations. And what we're going to be doing through this is solving equations for variables, so isolating for variables and then solving for that value. We're going to deal with some word problems, and then we're going to deal with some fractions as well, and bring up some terminology from number sense, things like LCMs and GCFs once again. Okay, so we start off with number 1 here, which is solving equations, 2 steps solve for x. Okay, so what we're going to want to do is we're going to want to isolate for x in this case, which will give us some specific value. When they say solve an equation, we want to solve it for a specific unknown variable. So here's what we're going to do. In this first problem here, we realize we have some term on the outside and it's being multiplied to something in the brackets here, more specifically a binomial or something with 2 terms. So what we're going to do here is we're going to expand this where we multiply 3 into both of these first 2 terms here. Now, the result is going to be, if I multiply this, it's 3 times 2x, which is 6x, 3 times 5, which is 15, and I guess I shouldn't put an equal sign here because it's right in the middle actually, is equal to 4x plus 7 minus x plus 1. Now, what we're going to do here is we're going to simplify our right-hand side because we see that there's terms that can come together on this right. So I'm going to rewrite 6x plus 15 is equal to 4x minus 1x, that's equal to 3x, and then 7 plus 1 is going to be equal to plus 8. Now, we want to isolate x on one side and all the numbers on the other. So what I'm going to do is I'm going to subtract away the 3x. I'm going to minus 3x minus 3x. That's going to cancel it from the right-hand side and then leave me with 6x minus 3x, which is 3x, plus 15, which is equal to 8. Now, our last and final step is to say, or we will have one more step beyond this, but what we want to do is we want to take away the 15 from this side here, minus 15. Now, what we're going to get is we're going to get 3x is equal to 8 minus 15. Well, that's equal to negative 7 because we're taking a positive number and subtracting away a larger number. So we know this is going to become negative. Our very last step here is to say, hey, we need to divide both of these by the coefficient that's on x. Therefore, x is equal to negative 7 over 3. There's your final solution when you solve for the equation. Okay, now we go over to this one here. Now, instead of just having one distribution, we have 2. We have to distribute this number and then distribute this number on the right-hand side of the equal sign. Okay, so starting with the left-hand side, 4 times negative x, a positive times a negative gives us negative 4x. Then we go 4 times 2, which is plus 8. This is going to be equal to, remember, if we have a negative on the outside, it's going to flip the signs on the interior. Negative times negative becomes a positive 2x. Negative times a negative 19, that's going to equal to a positive, and then 2 times 19 will give us equal to 38. Okay, now, yet again, we want to isolate for x on one side. What we could do is do all the x's to one side such that they're positive, or we could subtract away the x's and have them negative and just divide by the negative coefficient. So there's no real right way to do this. We could make the x positive right away. We could keep it negative, whatever. What I'm going to do is I'm going to add 4x across to keep our x's positive because I don't want them to be negative. I mean, they could be, but in this case, I don't want them to be. 8 is equal to 6x plus 38. And now what I have to do is subtract away this 38 from both sides. Because when I subtract away the 38 from both sides, it cancels here, just like the 4's canceled above. And now I get 8 minus 38 is equal to negative 30, which is equal to 6x. And this is our last step always in equations, is saying if we have a coefficient attached to that x, we want to divide or do the opposite operation. The opposite operation of multiplication is division, and therefore negative 30 divided by 6 is equal to negative 5, which is equal to x. Now, we could easily just reorder this such that it's x is equal to negative 5, and that means the same thing. That's more common on like a multiple choice, is it for it to be written like this rather than written like this. Okay, now solving equations dealing with fractions. So now what we have to do is say, okay, if we have a fraction, we don't want to have anything in the denominator. We want those fractions gone. So what do we have to do? We have to figure out what the LCM is. So the LCM is the first number that both of the items in the denominator multiply to, or the 3 items in the denominator multiply to. If I look at this, 5 and 4, what is the first number that both of them reach? Well, they both first multiply to make 20. That's their LCM, or the first number they can both multiply to. So what I'm going to do here is I'm going to multiply both sides of this equation and the entire sides of these equations by 20. Okay, if I multiply the left-hand side by 20, I have to distribute the 20 to both terms. Therefore, this is going to become 20 divided by 5 is 4, and 4 times 3 is equal to 12, and that's going to have an x here. So I took the 20 divided by 5, multiplied it by the 3. Now I go 20 times 2, which is equal to 40, and this is equal to 1 over 4 times 20, or 20 divided by 4 is equal to 5. Okay, now we want to isolate x, so what I'm going to do is subtract away the 40 from both sides. When I subtract away the 40 from both sides, I'm going to get 12x is equal to negative 35. And then from here, what I'm going to do is take the coefficient of whatever that x term is and divide it. Coefficient of the x term, divide it. Therefore, I get x is equal to negative 35 over 12. Now, if we could reduce this, we would. So in this case, I don't believe there's something we could reduce it by. Simply what we could do is figure out, oh, okay, well, if there's something that they both would share a common factor, let's say like 2, 3, 5, something like that, we could do this. But in the case of it ending by 5, we would most likely assume that these both wouldn't divide. So our final answer would just be this. Okay. Now we go to our second example. We have 3 numbers in the denominator. The nice thing is 2 of them are actually the same number. So what is our LCM? It's the most regardless of shared. So what we're going to look at this and say, well, the most amount of 5s that are shared is 1, and the most amount of 3s that are shared is 1. Our LCM is simply just multiplying one of each of those terms that appear in the denominator, because we don't want to do repeats. So our LCM is equal to 5 times 3, which is equal to 15. So remember, LCMs, you're not going to put in the repeat. You're just putting one of each of those items that appear in the denominator. Now, just like we did in the last problem, we're going to surround everything on both sides in brackets as the following, and we're going to multiply both by 15. When I do that, I have to distribute this 15 into both terms, meaning it's 1 over 5 times 15, which is equal to 3, and then there was an x attached by multiplication, plus 15 times 1 over 3, or 15 divided by 3, is 5. And this is equal to, now, when we multiply something to something with a coefficient like this, it is only getting multiplied to this term here alone, because that term then would distribute to the next 2 brackets. So what we do is, anytime we have something like this, and there's a term out front with some multiplication, we're just multiplying that LCM to the coefficient term. 2 over 5 times 15, or 15 divided by 5, which is 3, times 2, which is equal to 6. And this has an x plus 4 in brackets. Remember, we just leave that alone. If there's a coefficient term, we only multiply that LCM to the coefficient. Now, it's 3x plus 5 is equal to, I'm going to distribute the 6 to both terms, so it's going to be 6x plus 6 times 4, which is 24. Now we have to isolate for x. What I'm going to do to keep the x's positive is I'm going to subtract away the one that's less. Now, I could go the other way and subtract 6. That would equally be fine, and we get the same solution. This is going to leave me with 5 is equal to 3x, because 6x minus 3x is equal to 3x plus 24. And then one of the last steps here, I'm going to have to take away that 24 to leave the x alone. When I do 5 minus 24, well, the result is equal to negative 19, which is equal to 3x. And then my last step here is to divide both sides by 3. And therefore, my answer off to the side here is going to be x is equal to negative 19 over 3. Now, what I want you to recognize is that 19 is a prime number. So if you see a prime number, most likely this isn't going to reduce, because prime numbers can only divide by itself, or 1. So there's no possible case this would divide. And furthermore, 3 is also a prime number. So if we have prime number over prime number, there's just no way this is going to reduce further. All right, solving with a denominator or some variable in the denominator. Now, these ones are going to work very similar to the LCM. What we're going to do is we're going to have to realize whatever's in that denominator, we have to multiply to both sides. So the first one's actually quite simple. All we have to do with this one is say, if that x is in the denominator, I'm just going to multiply it out of the denominator. So when I multiply it out of the denominator as follows, well, it's going to cancel on the left-hand side here. I'm going to be left with negative 12 is equal to 3 times x. And then just like we did in the previous problems, if I want to solve for that x, what do I have to do? Divide by that coefficient. This will always typically be the last step in these equations. Now, negative 12 over 3 is equal to negative 4, because a negative over a positive number is going to give me a negative, and there we go. All right, similar to last problem, what we're going to do is we're going to multiply both sides by whatever's in the denominator for that variable, negative x. Negative x. We're going to multiply it to both sides. And to avoid confusion, I'm going to make sure that's in brackets, and I'm going to make sure that's in brackets to symbolize that all of that is being multiplied. Well, we know that by distribution, when I distribute this to both terms in the bracket, it's going to cancel that denominator. It's going to cancel that negative x out of the denominator. I'm going to get 24. And then negative x times 4 positive is a negative 4x is equal to 10 times a negative x, which is negative 10x. And now, if I want to move this 4x across, what I can do is add 4x. Add 4x, because I'm always thinking about these as opposites. If it's being subtracted, it's being added. If it's being added, it's subtracted. I'm going to have this is 24, which is equal to negative 10x plus 4x. This is a greater negative number than a positive number. Therefore, I get negative 6x. And when I divide away this entire coefficient on x, which is negative 6, I get my answer is 24 divided by negative 6. Therefore, x is equal to 24 divided by negative 6, which is a negative 4. Okay. Now, we move on to this next example. The only difference is now we have two variables going on, but they're the same variable. Nice part about this is that we can just multiply both sides by what we consider our LCM. Our LCM is simply just x, because it's the one thing that appears in the denominator, so we're just going to multiply both sides by x. Okay, when I multiply both sides by x, I need to remember that this distributes. It distributes to both terms that are on the sides there. So when I do 2 over x times x, the x's eliminate. When I do x times negative 5 over x, those x's eliminate. And here's what I have left. 2 plus x times 8, which is 8x, which is equal to negative 5, because the x from the denominator canceled, 1 times x, which is plus x, because we don't need to write that coefficient. I mean, we could, but it's just kind of an extra here. Now, what I'm going to do is keep my x's positive. How I'm going to do that is I'm going to subtract away the 1x from this side, subtract away the 1x from that side. That's going to cancel it from the right-hand side, and I'm going to be left with 2 plus 7x is equal to negative 5. From here, what I'm going to have to do is subtract away the 2, because my goal is to isolate for this x. When I do that, the 2's go away, and I have 7x is equal to negative 7. And lastly, I have to divide by whatever the coefficient on my variable is. In this case, it's 7. And therefore, what is my x value? X is equal to negative 7 over 7, which is negative 1. Because a negative divided by a positive gives us a negative. Similarly, when you multiply a negative by a positive, it gives you a negative as well. All right, now, very similar to the last problem, same idea. We're just going to multiply everything by that LCM, which in this case is x. When I multiply everything on both sides by x, we're going to see that the x on the left is going to eliminate, because it's x divided by x, which will eliminate, and I'm going to be left with negative 9 minus 7 is equal to, now I have to distribute this x on the outside. That's going to be x over x, which eliminates that x and just leaves me with negative 10 plus 3x. Okay, on the left-hand side, I'm going to combine those two terms together. Negative 9 minus 7, those can come together. They're two constant terms. Negative 7 minus another negative 9 is going to be equal to negative 16, which is equal to negative 10, and then plus 3x. Now, the x is positive, so the nice thing is I'm just going to add the 10 from the right-hand side to get it away. And when I do negative 16 plus 10, I get negative 6 is equal to 3x. And then just like in the last problems, and I'm going to cross out those 10s just to make sure they're gone. Just like the last problems, we always know that these are typically going to end with me dividing away a coefficient that appears on x, or whatever the variable is. And therefore, my x is equal to negative 6 over 3, which is equal to negative 2. All right, solving equations with complex fractions. Complex fractions, they like to throw out that word of complex. Complex just means that we have to deal with multiple terms in the numerator with a little trickier of an LCM. That's the only difference here. So what I want you to realize is that if I look at the denominator here for this first one, 3 and 2, what is the first number both of them multiply to? Well, their LCM is just simply the product of those numbers, 2 times 3, which is equal to 6. Remember, we don't want to repeat, so if there was multiple 2s or 3s, we just leave it as that. Now, we have, if I multiply both sides by that LCM, I get 6 and 6 here. And when I multiply that into the fraction, 6 divided by 3 is equal to 2. So I'm going to cancel both of those out and write a 2. 6 divided by 2 is equal to 3. So here's what my next line looks like. 2 times 4 minus x is equal to 3 times 3x plus 4. Now, I'm going to distribute each coefficient into the binomial. Each coefficient into the binomial, here's what I get. 2 times 4 is 8, minus 2 times a negative x is negative 2x, is equal to 3 times 3x is 9x, 3 times 4 is plus 12. Now, we've seen this equation lots in the last examples. What we have to do is isolate for x. I'm going to add the 2x across just to keep the x's positive. So if I add the 2x across, this is going to leave me with 8 is equal to 9 plus 2x, which is 11x, plus 12. And now I have to subtract away this positive 12 from both sides. And I'm going to get an answer of negative 4 is equal to 11x. When I divide by that coefficient on the x, which is 11, therefore my answer for x is equal to negative 4 over 11. Remember what I said about prime numbers. If you see a prime number involved in the fraction, typically that's not going to reduce. Unless this was like 11 over 11 or some divisible number by 11, something like 22, typically this isn't going to reduce. And if we look at this, we have an even over an odd. Typically those won't reduce. That's another thing. Unless they're quite large numbers and you can find some factor in them, this would be common. All right, this example looks super complicated on surface level, but let's break it down. LCM, if I look at the denominator and I look at all those numbers going on, 4, 5, and 20, well, the nice thing is they actually told us the LCM right in the problem. What is the first number that 4 and 5 and 20 all multiply to? It's 20. It's just the number itself because we know 4 times 5 can be 20, or both 4 and 5 can multiply to get to 20. So we're just going to say our LCM is 20, and I'm going to multiply both sides by 20. So I take everything on both sides and multiply it by 20. On my left, I'm going to distribute that 20, and on my right, I'm also going to distribute the 20. But we remember, 20 divide. So if I start at this first part here, 20 times this first fraction, that's going to be 20 divided by 4, which is 5, multiplied by whatever was in the numerator. We then add, well, 20 divided by 5. So if I consider this fraction here, or this multiplication, 20 times something over 5. Well, 20 over 5 is 4, and it's multiplied to whatever is on that interior. And this is equal to 20 divided by 20 on my left hand or my right hand side equation. That actually just simplifies down to 1. It goes away. So now I'm just left with 2x plus 1. Okay, let's expand this. So we're going to expand the 5 into the brackets. That becomes 5x plus 25 plus 4x. 4 times a negative 3 is negative 12, which is equal to 2x plus 1. Okay, we're going to combine our like terms because we have a few like terms on this left-hand side. Let's put them together here. So 5x plus 4x is 9x plus 25 minus 12 is equal to 13. Which is equal to 2x plus 1. Okay, to keep the x's positive, I'm going to subtract away the smaller amount of x's. And when I subtract them, it's going to eliminate from the right, and I'm going to be given 9x minus 2x is 7x, which is, and then plus 13 is equal to 1. Now, I have to get rid of that number that's attached and use the opposite operation, so subtract. I get 7x is equal to negative 12. And then from here, I'm going to realize that I have to divide away that 7. That's the coefficient on the x term. And therefore, my x answer is equal to negative 12 over 7. And this can't reduce because what type of number is 7? Well, 7 is actually a prime number. It's something that can only be multiplied by itself or 1. There's not like 2 times 3 equals 7 or some number like that. It can only be multiplied by itself or 1 or divided by itself or 1 more specifically. So this fraction won't reduce in this case. All right, isolating equation with multiple variables. If we want to isolate for x in all of these, well, all we have to do is realize that there's some other variable going on. It just needs to be on the opposite side of x and isolated. Okay, so in the first equation here, if we want to isolate for x and our goal is to just have x on one side all by itself, well, we only have one step here. I just need to take away that 2 that's being added to the x there. Therefore, x is equal to y minus 2. Because when we subtract away that 2, it's going to cancel, and I'm just left with this equation as isolated for x. Now, the next part actually looks very similar, just has a couple more steps here. I'm going to add this 2 across if my goal is to isolate for x. That's going to give me y plus 2 is equal to 2x. But now I have this coefficient that must be divided and divided to everything on both sides. Therefore, when I divide, it's going to cancel from the right. I could draw an arrow through these two. It cancels here. I'm given x is equal to y plus 2 all over 2. Now, you could separate this into their own fractions as y over 2 and plus 2 over 2. So I'll put that right below here just so we can see it. Y over 2 plus 2 over 2, which, of course, 2 over 2, if I write 2 over 2, that could simply just simplify down to 1. So that's another way to write this solution. But however, the top one, if you did that in the written response, I'm totally fine with that. That looks like a good answer to me. All right, we're wanting to isolate for x in this one. Just like the last couple examples, we're going to subtract away the 6, or whatever the constant term is. Y minus 6 is equal to x over 2. Now, this is the first time we've seen this. If I want to undo the operation of something being divided from x, well, if it's being divided, to undo that, I have to multiply it. So I'm going to multiply it to both sides like this. That's going to cancel the 2 from the right and leave me with 2 times y minus 6 is equal to x. Now, just like the last problem, we could do one more step to simplify it. I could say 2y minus 2 times negative 6, which is 12, is equal to x. So if I wanted to expand that tooth into both the brackets here or into the brackets, I could do that. However, for this example, it might not be necessary, but I would say this is probably a more simplified solution for sure. So if they want you to go all the way with this and say isolate it for it and simplify if possible, this might be the best solution for you. All right, now we have a pretty complicated equation here, or what seemingly looks complicated, but let's break it down. We want to isolate for x. I'm going to start by subtracting away that 2y. It's being added, I'm going to subtract it. When we subtract it, it's going to cancel from the right, and 3y minus 2y leaves me with 1y. Now, we know that the y doesn't have to be included with that 1 there because anything times 1 is just itself. I'm going to be left with 5 over 2 times x plus 7. If I want to get rid of that 2 from the denominator, I'm going to multiply both sides by 2. This will give me 2y is equal to 5 because the 2 in the denominator is going to cancel. 5 times x plus 7. I'm going to divide both sides by that coefficient term being multiplied. So everything's going to be divided by 5. That's going to leave me with 2y over 5 is equal to x plus 7. Lastly, to isolate for x, I'm going to subtract away the 7 from both sides. And therefore, x is equal to 2y over 5 minus 7. There we go. So it's just realizing that we're undoing a bunch of operations. If it's adding, we're subtracting. If it's dividing, we're multiplying. If it's multiplying, we're dividing. We're doing everything in opposites to undo what the equation looks like to get us to our new spot. All right, in this next one, we have 4 variables. We have k, m, and x. If I want to isolate for x here, well, my first step is I want to get x out of the denominator because to isolate for x means it should be in the numerator. So we treat it as an LCM. I multiply both sides by that x. Okay, when I do that, I'm going to be left with x times k is equal to, and remember, when I take an LCM and multiply it to both sides, it multiplies to everything on both sides. So it's going to be x times m plus, we know these two x's are going to go away. An x divided by an x is 1. And this is n. Okay, now I'm going to subtract away the x times n, subtract away the x times n. This might not be obvious of why I'm doing that, but here's why. If I go x times k minus x times m is equal to n, well, now we bring in the terminology of a GCF. What is the GCF, or the thing that is shared in this equation here? If I look at this line, what is shared? It's the x. I bring that out front. X times k minus m is equal to n. And now, if two things are being multiplied like this, what can I do? I can divide. Divided by k minus m, divided by k minus m. Therefore, the value of x here is equal to n over k minus m. Very similar to a physics problem, for sure, is where you have multiple variables and they may ask you, hey, isolate for this variable and then apply that to a certain example. All right, lastly, you should recognize this equation from our last unit equations. It's y equals mx plus b. It's the equation of a linear line. Now, that's besides the point because we still want to isolate for x. We're going to subtract away b, subtract away b. That's going to leave us with y minus b is equal to m times x. And we know when anything is being multiplied to that x, we want to divide by it. So I'm going to divide both sides by m. And therefore, I get x is equal to y minus b over m, because we know that those m's cancel. As soon as we have something that's the same thing over each other, or one in the numerator, one in the denominator, the same term, they cancel down to m to the 0, which is technically 1, or we could just say they're 1 right away. So therefore, that is our solution here. All right, now solve the system of equations. System of equations is done by substitution, which in 10C we'll learn a method called elimination. But for what we did in Math 15, we just purely did substitution. Now, here's the big key. Answers must be in an ordered pair of x, y. What is an ordered pair? It's a specific point on the Cartesian plane where two lines overlap. So you could think about it like this. If I just did it off to the side here, this may be a little small. If I'm looking at the Cartesian plane, which we talked about a lot in class, x and y, and I have a line like this, and then I have a line like this, the solution or the ordered pair is their crossover. It's the x and y that represent that specific crossover. So when we solve these and get an ordered pair, what are we doing? We're finding an xy that represents some crossover point. Okay, so how we do this using substitution, we want to realize that as long as we have one of the variables isolated, well, what we can do is take everything that's represented by that value or variable and sub it in above. So I go, because I know that y equals -3, well, then it must be that -3 is equal to 7x minus 10. I can now say plus 10 to get rid of that 10 and isolate for x. I get 7 is equal to 7x. I divide both sides by that 7, and therefore I get an x value equal to 1. Now, this isn't a full ordered pair or a full solution. What I need to do now is say, well, what was y? They actually gave us the y. It was -3. So therefore, when we go to our final solution, therefore the ordered pair of x and y is equal to 1 for x, -3 for y, and that would represent our solution. Now, if you just put this point here, perfect. If you just do that and you write out the ordered pair, you don't technically need this. However, this is a good level of organization, but if you just want to put the answer, that is totally fine. Okay, now in this last one, they kind of give us a different approach. They say, what if we isolate for x instead, and then we use that x value and sub it in the top equation there? Well, here's what it's going to look like. I'm going to write out 3 times, what was all of x equal to? 2y minus 3. We take everything x was equal to, 2y minus 3. I've substituted everything here into the value of x. So this is going to be minus 7y is equal to -14. I'm going to expand out that monomial by binomial, or do this expansion. That's going to be 6y minus 9 minus 7y is equal to -14. I'm going to isolate for the y, but before I'm going to do that, I'm going to combine like terms. 6y minus 7y is -y minus 9 is equal to -14. I'm going to add the 9 across. And when I add the 9 across, here's what I get. -y is equal to -14 plus 9 is -5. And then lastly, we have that negative coefficient, which is technically a -1. We're going to divide by it. Now, equally, what you could do is multiply by a negative and just get rid of that. But I always want you to get in the habit of, if it's being multiplied by a negative, you divide to get it away. Now, y is therefore equal to 5. Remember, this is only a partial solution. We need both x and y. So here's what I do. I take the isolated equation for x and put in the y value we just got. So therefore, x is equal to, well, what's the equation? It's 2 times that y value, which is 5, minus 3. That's equal to 10 minus 3. And then therefore x is equal to 7. And as an ordered pair, our last piece would to say our xy ordered pair as a solution is, well, our x value always comes first and it's 7. Our y value is 5. So there is the coordinates of the specific overlap where these two lines intersect one another. Okay, now lastly, this one's a little tough because rather than just being given an isolated x or y, they give us two equations where neither x or y are isolated. So what we're going to do is we're going to pick one of them, and specifically, I'm going to pick the one that already has an x alone. Because if we look at this, we see that there's a 2 attached here, a 4 attached here, a 6 here. Those would require more algebra than just simply taking the first equation and isolating. X minus 2y is equal to -6. I'm going to add that 2y across. Add the 2y, add the 2y. This is going to give me an equation of x is equal to 2y minus 6. Now, I want to use this equation with the other equation in order to solve for x. So what I can do is now say if x is equal to all of this, I'm going to take all of this and plug it in for the x there. So we have x is equal to 2y minus 6. Therefore, 4 times everything x equals 2y minus 6 plus 6y is equal to 4. I expand the brackets on the left here. So I expand by multiplying it into the brackets. 8y minus 4 times -6 is -24 plus 6y is equal to 4. And now I get 8y plus 6y is 14y minus 24 is equal to 4. If I add the 24 to both sides, add 24, add 24, this is going to be equal to 14y, which is equal to 28. And lastly, just like we've done all throughout this review here, we're going to divide by whatever coefficient is attached here. So this is going to become y is equal to 28 over 14, which is 2. Now we have to recognize that this is only a partial solution. To get the full solution, we have to take whatever we got for y and plug it in for the one that had x isolated. So if I want my full solution, I'm going to go x was equal to 2y, which is times 2, minus 6. Therefore, x is equal to 4 minus 6, which is equal to -2. Therefore, my xy ordered pair is equal to, and I'll draw the little arrow below, my x and y is -2, because that's the x, +2, which is the y. There is my solution here. All right, translating into algebraic expressions, we're going to let x be the variable that we describe. So they're going to give you a statement and say, well, what's the equation that represents this? Okay, well, if we want to create an algebraic expression that would represent this, well, what we're going to do is we're going to say, okay, whatever words that are being used here, we have to involve some variables. So 1/9 of a number. When they say that classic phrase of a number, what are they saying? Let that number just be x. We don't know the number, so we're just going to say let that be x. 1/9 of that number, so 1/9 times x is increased plus by 17. So we go 1/9 of a number, which in this case is just x, plus 17 because it's increased by that. Okay, 4 less than 11 times a number. Well, remember that classic phrase, a number, what are they referring to? That's our x. So what we have to do is we have to say 11 times whatever that number is minus 4, because it's 4 less than 11 times that number. Quadruple the sum of 2 times a number and 8. Okay, so here's what we want to do. They say quadruple. What does that do? It's a multiple of 4. And we're going to put that aside for a second because they say it's quadruple the sum of a couple things that are happening here. 2 times a number, which is 2 times x, because we don't know what that number is, but the sum refers to it being an adding of 8. The sum of 2 times a number and 8, and it's multiplied by 4, or it's quadruple this. So it would be this. All right, 9 less than 8/13 of a number. 8/13, well, let's translate that into a fraction. It's 8 over 13. And when we say 8/13 of a number, well, that number we don't know is x. We're going to multiply it to that fraction. And they say it's 9 less than that. So what we're going to do is say subtract away 9. All right, word problems of various types. Word problems are always going to say, well, what if I give you a certain setup, and then we have to use that setup in order to solve for some missing piece along the way. In the first problem, they say, if I give you this tube, and then at this split point, we can measure it as 2 times x inches for that first component, and then we can say that the other piece is 26 inches, but the total is 54. What is the value of x? Here's what we have to do. We realize that this plus this equals the whole distance. So what are we going to do? We're going to say 54 is equal to 2x, which is symbolic of the first piece, plus 26 inches, which represents the other piece. All right, now we go 54, and what we're going to have to do is if we want to solve for x, we have to subtract 26 away. And when we subtract 26 from both sides, we know that it eliminates on the right-hand side, so we can x that piece out. But then 54 minus 26 is equal to 28, and we can write that on the left-hand side. 28 is equal to 2x. Just like we did all the way through equations here, we are going to divide by whatever is attached to the x, and therefore, x is equal to 14. Now, what I could do is I could go back through this and plug x in and just confirm that this is true. However, I'd be pretty confident to say if I take this x that we got and plug it back in here for x, we're going to get 54. But if they ask you to check, that's how you do it. You take whatever number is and you just plug it back into the equation. But some of the problems will just say, what is the value, and then end there. All right, Lily's aquarium has 4 more than double the number of fish in John's aquarium. Let F represent the number of fish in John's aquarium. Write an expression that describes this. Okay, so right away, we want to make a statement in terms of comparing Lily's to John's aquarium. Well, Lily's, so I'll just short form it like this. Lily's is equal to, well, they give us specific instructions here. They say it's 4 more than double the number of fish in his aquarium, where F is the fish in his aquarium. So what are we going to do? Well, I'm just going to write out F, which is symbolic of John's. And we know that it's double whatever are in John's tank, which is the F, double F, plus 4, because it's 4 more than that. So this would be our statement here, where we know that F represents the number of fish in John's, and then the specific instructions say that Lily's has 4 more than double what John's has. And then all we need to do is just write the expression, don't need to solve it. That's all they asked for here. All right, the length of a football field is 30 yards more than its width. Write a mathematical expression for the length of the field using W to represent the width of the field. And then what is the length of the field if the width is 53 yards? Okay, so what they're doing is they're saying, let's create an algebraic expression. What I would always recommend is for these pieces here, draw a diagram. A diagram is always critical, especially when they're like describing details. In 10C, this is going to become huge too. The length of a football field, which I'm going to consider this as our length. This is our length. This is our width. This is our width. Okay. The length of a football field is 30 more than its width. So therefore, length is equal to width plus 30, because whatever the width is, we just add 30 and that's going to give it to us there. So write a mathematical expression for the length in terms of that. Perfect, we've done that. What is the length of the football field if the width is 53 yards? Well, this is a perimeter equation. So if this part satisfies A, then for B, what we're going to have to do is say that the perimeter, which is equal to, okay, and actually in this case, they might not even ask us to do perimeter. What is the length of the field if the width is 53 yards? All we have to do is take our given equation of length is equal to width plus 30. And if they say that the width is 53 yards, all we have to do from here is say length is equal to 53 plus 30. Therefore, the length is equal to 83 yards, which I'll short form as YRDS, 83 yards. All right, the sum of three consecutive integers is equal to negative 39. Determine those integers. What are integers? Well, anything that's an element of the integer family is things like -2, -1, 0, 1, 2. It's all the numbers that are whole numbers, positive or negative, including 0. So what we're going to do is we're going to take that idea of what an integer is, where it's all of the whole numbers, negative or positive, including 0, and we need to symbolize what each of these would be. So let's say I chose, in terms of variables, 0 to be represented by x. Well, then to get from 0 to 1, what would I have to do? I would just have to add 1. So my next term would be x plus 1 in the consecutive integers. If I want to go from 1 to 2 from here, well, what do I have to do to x plus 1? I just have to add another 1. So it becomes x plus 1 plus another 1. So my consecutive integers are therefore x plus 1, and x plus 1, which is x plus 2. So we choose a number, which in this case would be x or whatever variable, and then we add 1, add 2, add 3, and we could continue that on. Now, I could go in the reverse direction. I could also equally say x minus 1, x minus 2. That would also be okay. But for this problem, I'm going to go the positive direction. So we've set up what our consecutive integers are, or numbers that come one after the other, and they say that negative 39 is the sum of those consecutive integers. So x plus 1 plus x plus 2. If I take all those three consecutive integers and add them together, I'll get negative 39. So negative 39 is equal to, how many x's do I have on the right? 1, 2, 3. So I'm going to write this as 3x. How many constants do I have? Well, I have 1 and then 2. If I add those together, that's going to be plus 3. Okay, now my job is similarly to whatever else I did in equations. I want to isolate for the variable minus 3, minus 3. I'm going to continue this over here on the top. We get negative 39 minus 3. That's equal to negative 42, which is equal to 3x. And now I know if I have a constant term or a coefficient on the x, I need to divide it. And so I'm going to take that 3 and divide it from both sides here. That's going to eliminate it from the variable, meaning x is equal to, in this case, negative 14. Now remember, this was only one piece of the solution. That's the first consecutive integer. To get the next one, I have to go x plus 1, and x plus 1, or negative 14 plus 1, is equal to negative 13. And then my last number in this is x plus 2, or the third consecutive integer. If I go x, which is negative 14, plus a 2, that's equal to negative 12. So here are the answers, and I'll highlight all three of them. 1 consecutive integer, 2 consecutive integers, and 3 consecutive integers. The hardest piece about this problem is identifying what is a consecutive integer. Well, start by just identifying whatever the first one is, x or some variable, and then add 1, add 2, add 3 as you go down the line, or in the reverse direction, it could also be true. If I wanted to go from 0 to negative 1 to negative 2, what am I technically doing? Well, I'll do it in blue here. It would be x minus 1, then x minus 2, and then on and on and on the other way. So however you want to visualize this. All right, a jar contains this amount of dollars in toonies and quarters. So $38.50 in toonies and quarters. Well, a toonie is the value of $2. And then a quarter is the value of 0.25 cents. Okay, so there are 6 times as many quarters as toonies. Determine the number of toonies and quarters. Okay, so what we're going to do here is we're going to set it up as the total amount, $38.50. And this is going to be equal to, well, now we have to identify some variables here. We're going to say let the certain amount of, in this case, which one is the descriptor? They say there's 6 times as many quarters as toonies. So toonies are going to be described as x. So let t be equal to x. And then let the amount of quarters, or q, be equal to 6 times that amount of toonies. So 6x. If I want to say the total is equal to, well, the total is equal to the value of a toonie times what a toonie is equal to, which in this case, we were letting it being symbolized by x, or the number of toonies that are involved. So 2 times the number of toonies that are involved or equal to x, plus 0.25, which is the value of a quarter, times 6x, which means that we have times the amount of quarters than we do of toonies, because toonies are x, so to get the quarters, we have to multiply by 6. Now, this is going to be equal to, if we multiply this out, we're going to get equal to 3850 is equal to 2x plus 0.25 times 6 is equal to 1.5x. Okay. Now, we're going to add the like terms together. So we're going to go 38.50 or $38.50 is equal to 3.5x. And now, just similar to what we do all the way through equations, I'm just going to divide by that coefficient. And we say that 38.50 divided by 3.5 is equal to 11. X is equal to 11. And I'll make sure for consistency, I have this in black here. X is equal to 11. Well, X, how many was that? That was the number of toonies. So in brackets, I'm just going to write toonies. How do I get the amount of quarters? Well, remember, quarters were 6 times X. And if X is equal to 11, it's 6 times 11, which is equal to 66 quarters. There we go. So we would say therefore, and these are our two solutions here. This amount of toonies, which I'll highlight the whole thing, this amount of quarters. All right, we're going to describe a triangle and its perimeter in terms of, hey, if you're given the perimeter, what are all the different sides here? So what I want to do is I'm just going to draw a triangle right away. As soon as they involve a shape, I'm just going to just draw it out. Okay, now I'm going to provide the context to this triangle. Side 2, which I'm just going to label them here. Actually, I'll label them as I go through them. Side number 2 of triangle is 1 meter longer than side number 1. So let's let side number 1 be this side here. And side number 2, which I'll put numbers here, side number 2 is going to be here, and it's going to be side number 1 plus 1. And then they say that if side 3 is 1 meter longer than side 2, what is that technically saying? Well, this is side 3. It's saying we have x plus 1, which is side 2, plus 1. Well, what is that equal to? It's x plus 2. Now, oddly enough, that describes consecutive integers as well. So we shouldn't be surprised if we see consecutive integers as our values for the perimeter here. They say if the perimeter of the triangle is equal to 33 meters, what is each of the side lengths? Well, perimeter, remember, perimeter is adding all of those outside lengths together. It's adding 1, 2, and 3 all together as a sum. So what I'm going to do is say perimeter is equal to 33 is equal to x plus side number 2, which is x plus 1, plus side number 3, which is x plus 2. So if we need to be more clear, this is side 1, 2, and 3. Okay, when we add them together, we get 33 is equal to, how many x's do we have? 3 x's total. How many numbers do we have? Our constants? 3. This is going to be equal to, in this case, 30 is equal to 3x. And then I divide both sides by 3. Divide both sides by 3. And therefore, x is equal to 10. Now remember, that's only side 1. How do I get the other sides here? What do I have to do? I have to go x plus 1, which is side 2. X plus 1, or 10 plus 1, is 11. X plus 2 represents the third side, and that's 10 plus 2, which is 12. So these are the 3 side lengths, 1, 2, and 3. Or pictorially, I could go back on my diagram and say this is symbolic of 10, this is 11, and this would be 12 as my very bottom. All right, Mina is 3 years older than Noor Eslin. Twice Noor's age, minus 7 is Mina's age. How old are Mina and Noor? So what I'm going to do is I'm going to say, okay, well, if they said that Mina is 3 years older than Noor, I'm going to put a statement here. Let x equal Noor. And then we're going to say let Mina, or let x plus 3 according to the instructions, because they say Mina is 3 years older than Noor. We're going to say x plus 3 is equal to Mina. Now, reading furthermore into this instruction, twice Noor's age minus 7 is Mina's age. Well, here's what we do. If Mina is equal to x plus 3, and they give us a descriptor of Noor's age in comparison to this, twice Noor's age, which he was equal to x, so 2 times x, and then they say minus 7 in the instructions is equal to Mina's age, and below I'm actually going to put those. This is Mina, and this is Noor. Now all we have to do is solve for x, which is going to represent Noor's age, and we'll also be able to find Mina's age from here. Let's do it. So what I'm going to do is I'm going to say my first step is going to be subtracting away x from both sides. It will eliminate from the left, leaving me with 3 is equal to 2x minus x is 1x, and then minus 7. From here, I know that I have to add 7 to both sides because I want to isolate for x, and therefore I'm going to get an x equal to 10. Well, what is this 10 symbolizing? It's symbolizing Noor's age. So I'll put Noor's age in brackets. What is Mina's age? Mina's age, therefore, is equal to x plus 3. And if x is 10, then 10 plus 3 is 13. And this is equal to Mina's age. So it's about looking at the problem and saying, well, if they tell us what Mina's age is in comparison to that person, or Noor in this case, and then Noor's age in comparison to Mina, well, let's put those on two sides of an equal sign and then solve for that x. Whatever that x is, you have to clearly label. In this case, we clearly labeled Noor's age as the one that was being compared to Mina's right away. And so whatever one doesn't include a direct descriptor, in this case, Noor's age wasn't directly used as a descriptor, we're going to just set it equal to x. So one of the ages is x, the other one is x plus 3, and then we use those descriptors to cross over. Which question could correctly be answered by solving the following equation? So they give us this equation here, and they say we want to use these word problems to figure out which one could be using this equation to help them solve. Simon had 1/3. So if I look at the first one, Simon had 1/3 or 1 2/3 square meters of cloth to buy a baby's dress. He had 2 3/4 square meters of the cloth left after he made the dress. How many square meters of cloth did Simon use to make the dress? Now, this one seems okay because it says that he says that he originally has this total amount of material, but then uses and then has this amount left at the end. Well, here's a big error that goes on with this. They say that this is the amount that Simon had to use, 1 2/3, but then he had 2 3/4 left. That means he has more material at the end than he did at the beginning. That can't be true. Simon made a cardboard sign for B. Simon made a cardboard sign that was 1 2/3 feet long. Then he made a second sign that had a length that was 2 3/4 feet shorter than the first sign. What is the length of the second sign? Well, a lot of this is just seeming false right away because they say he made a cardboard sign that had a certain amount of material, and then the second one had a length that was this shorter than the other one. Well, in this problem, it's the same kind of concept that was wrong with A. If he has this amount of material that represents what he makes in the cardboard sign, it's this amount of feet long, and then all of a sudden the next one is 2 3/4 shorter than the first one, that means you're taking away more than what was originally used. That definitely can't be true. No way. Simon for C has a bottle with 1 2 liters of water. He uses 2 3/4 to make fruit juice. How much was left in the bottle? That's another one of those cases where it's like, if he has this amount and then uses this, well, how does that even make sense? Because he's taking away more than he started with. That doesn't add up. So C is gone, therefore D is true, but let's confirm that. So we know D is going to be the one that ends up being the truth, but let's see. Simon had 2/3 cup of flour left after he used 1 2/3 cup of flour to bake a cake. How much flour did Simon have before baking the cake? This one clearly seems okay because they say in the end he has this amount. Okay, so on one side of the equal sign, we should see that value. Simon had this amount after he made the cake. So this and this, because it was how much was left. Then he uses 1 2/3 cup of flour to bake a cake. How much did he have before baking the cake? Well, this is X. That's the amount before he started baking the cake. And then the amount he uses should be subtracted away, which is that 1 2/3, which is subtracted away. So that one clearly lines up here.